Okay, we're going.
Okay.
Fantastic, thank you. So welcome everyone. We are joined by Alex Simpson from the University of Ljubljana in Slovenia as part of our exchange in the project Computing with Infinite Data. Alex is visiting the University of South Africa in Pretoria at the moment, and this afternoon he is giving the first of two talks related to his visit on the mathematical theory of true randomness. Now, since Alex and I are in the same room, there will be just a second or two while I hand over to him. So I'm going to mute myself now. So Alex, welcome, and please take over.
Right, thank you very much, Petrus. Can you hear me? Excellent. Okay, so thank you for the introduction, and it's a great pleasure to be back in Pretoria after, well, 3 years or something like that since my last visit. Actually, what I'm going to talk about, I already talked about in Pretoria on my previous visit at the Florida campus. However, I have made progress on the topic since then, so this is an updated version. The title is both ambiguous and looks a little bit pretentious. It's ambiguous in the sense that you might say something like the algebraic theory of non-commutative idempotent semigroups is a mathematical theory of true randomness. I hope I haven't offended anyone by saying that. Of course, that's not how I mean the title. I mean trying to give a mathematical theory of what one might call, something that one might call true randomness, trying to understand the concept of true randomness. So in that sense, it sounds a bit pretentious. What I'm not claiming is that I have a true and final theory of true randomness, but the title is an honest title in the sense that my goal is to try and understand how one might give a mathematical theory of such a thing. Before going on, I'd like to thank the European project, the project Computing with Infinite Data, that is funding my visit to South Africa, and which the research has been carried out under that project. But actually this research goes back long before that. I've been doing it for essentially 10 years. I've been trying to do what I'm going to talk about today for more than 10 years. It's been a very slow program. I had a grant from the Templeton Foundation 10 years ago, whose goal was to develop this theory, but I didn't quite manage to do it in time during that grant. But anyway, so today I'm going to talk about where I've got to now. And I now think, compared with 3 years ago when I gave the talk at the Florida campus, I think I've developed a much more convincing theory. Okay, so as Pietro said at the start, it's actually going to be a talk in two parts. Today I'm going to go through the motivation for the theory, and then it's an axiomatic theory of randomness, and I'm going to present the main axioms for the theory. But beforehand, let's consider what we might mean by true randomness. So randomness in mathematics arises in sort of very many different degrees of randomness, if you like. So I've written out a sort of hierarchy here of notions of randomness. And at the top, in more ways than one, is what people call pseudo-randomness, where pseudo-randomness typically means spotting patterns in non-random mathematical situations or non-random mathematical structures, but patterns that would nonetheless be typically there if the structures had been generated randomly. This occurs very widely. These sorts of ideas occur very widely in mainstream mathematics, for example. In the prime numbers, there are results and conjectures that say that the prime numbers exhibit some typical properties of randomness. For example, even the Riemann hypothesis is equivalent to one such statement. And the notion of pseudo-randomness is also obviously important in computer science, where pseudo-random number generators are really useful in practice. And there's a whole beautiful mathematical theory of pseudo-random number generators, which is part of computational complexity theory. So kind of when one's looking at pseudo-randomness, it's just some aspects of randomness, not full randomness. But on the other hand, the fact that one's looking at weakened notions of randomness means that these ideas are really powerful and widespread, and occur throughout mathematics. And I've just put a list of some names of people that work in areas of mathematics where you could say pseudo-randomness is important in their work. And you might notice that these are all mathematical recipients of top mathematical prizes. So pseudo-randomness is really at the highest level occurs at the highest level in mathematics. But then going back to the turn of, well, going through history of mathematics, but certainly it was a topic that arose at the start of the 20th century, so more than 100 years ago. People were trying to make sense of truer notions of randomness, in the sense of randomness of data that is really random, in that it doesn't just exhibit some typical properties of randomness, it exhibits essentially all the properties one could possibly expect of randomness, so satisfies as many statistical laws as possible. And at the start of the 20th century, von Mises, somebody called von Mises developed an early version of mathematical probability theory based on such a notion of randomness as the primitive notion. That's now been, for a long time now, been superseded by Kolmogorov's measure-theoretic approach to probability theory. But Kolmogorov, as well as developing probability theory in the way it's done, in the way it's currently done, he also remained very interested in the notion of randomness throughout his life, and he developed an approach to randomness based on his algorithmic complexity, Kolmogorov complexity, and this then developed largely due to the work of Martin Luff and Chaitin and Schnorr that I mentioned here, into what's currently a very flourishing area of algorithmic randomness, where the idea is essentially that one looks at randomness in the sense of one views something as being random if all typical properties that can be specified in some computable way are satisfied. So if some data exhibits all computably specifiable typical properties. So that gives very strong notions of already a very strong, well, several different very strong notions of randomness, but still the typical properties that are satisfied still need to be given some description, normally some sort of computable description in some sense. A notion of randomness that's even stronger than that was developed by Robert Solovay as part of the techniques he developed to prove that the set-theoretic statement that all sets of reals are Lebesgue measurable is actually consistent with the axioms of set theory, as long as you weaken the axiom of choice to drop the full axiom of choice and weaken it to dependent choice. And his notion of randomness there is you're essentially working in a large model of set theory, but the model extends a a given countable model of set theory, and randomness means satisfying all typical properties that are specified in the core countable model of set theory. So these notions are all getting now relatively complex, but have we got to true randomness? Well, if you want to talk about true randomness, well, there's a question, or essentially the very question itself is, what do you mean by true randomness? There is no consensus agreement as to what true randomness means, or whether it even makes sense at all. There's of course, the physical question: does true randomness exist in the physical world? Perhaps via quantum mechanical measurements. So of course, I'm not going to address the physical side at all. So what I want to address in this talk is the question: can we make sense of a notion of true randomness in, if you like, the Platonic universe of mathematical concepts? So that in itself is already a very challenging question. And so that's the topic we address today. Before moving my slide, I'm just going to wanted to see if I can move my control bar around, but I can't, apparently. Okay, so to motivate where we're going, let's consider a very simple situation in which we've got two infinite sequences of fair coin tosses. So my fair coin tosses are going to be labeled by 0 and 1. 0 looks like a head, 1 looks like a tail. And the idea is we've got two such sequences generated by fair coin tosses, and they're independent. We've generated them independently from each other. And then here, we've got three statements, each of which are talking about the membership of this particular sequence R in a probability 1 set. So the first one says R belongs to the set of all sequences with R taken away from it, which is, of course, a false mathematical statement, trivially so. The second one says R belongs to the set of all sequences with the infinite sequence of zeros taken away from it. And the third one says R belongs to the set of all sequences with the independently generated sequence S taken away from it. So, as I said, the first one is a trivial mathematical falsehood. The interesting thing about the second and third of these statements is that, well, according to sort of standard mathematics, it doesn't make sense to ask the question, does R belong to, is the second sentence true or the third sentence true? We can turn it into a probabilistic statement that does make sense, which is considering R as a random variable, the second statement is almost surely satisfied, and the third statement is almost surely satisfied. And the notion of almost surely is in order to be able to deal with corner cases like the first statement, where something doesn't hold even though it's the membership of a random thing belonging to a probability 1 set. So the point is, these statements, the second and third one, are not normally considered as mathematical truths. But if one had a true theory of randomness, one would really like these to be very basic mathematical truths. So one would like to say, well, we've got our independently generated R and S, and so it should be the case that R is random, so it should just be mathematically true that it's not the constantly zero sequence, and it should just be mathematically true that it's different from S. So I want to turn statements 2 and 3 mathematical truths, but also do much more at the same time. And the idea for doing this is to include a primitive independence relation into the mathematical universe that allows us to state the assumptions here that we've got two sequences generated independently by random tosses of a fair coin. And In particular, introducing the independent relation is going to allow us to define a true notion of randomness. Before going on, for those of you, well, for those of you who know about it, and for those of you who don't, because it's some literature that's very interesting, I think. There was a very closely related program followed by Michiel van Lambaugen. I think there's an L missing there. In his PhD thesis, well, work that started in his PhD thesis in, I think, the late 1980s, but published in the Journal of Symbolic Logic in 1990 and 1992. So my development parallels his in some ways. It's distinct from it also in many ways, but rather than discussing the relationship as I go along, I'm going to discuss the connections at the end of the second talk. Right, so we're going to introduce an independence relation essentially into the mathematical universe. So we're going to work in, as a standard set theoretic, if you like, mathematical universe, and we're going to extend our vocabulary with an independence relation. So I'm going to write that x and y are just any elements of the mathematical universe. I'm going to write x is independent from y. With the intuitive meaning here, so the motivation is that the mathematical entities, x and y, could be obtained by two different mathematicians tapping into two independent random sources. So for example, doesn't really matter whether they're mathematicians or not, but anyway, two different agents, if you like, tapping into independent random sources. So for example, we could have one agent on the left here independently tossing a fair coin, and the sequence was indeed generated by coin tossers. Can't actually tell you if the coin was totally fair, but anyway, it looks reasonably fair so far. And another sequence generated independently from the first one by rolling a die repeatedly. So this was where I got to. One comment I want to make at this stage is that when you generate such data randomly, or whenever you only ever see finite portions of it, and so kind of we think of there being a whole infinite sequence there, and indeed mathematically I'm going to model it as an infinite sequence, but in some sense is what I'm going to call an uncertain sequence. There's some uncertainty in what it's going to be. That's one example of independence, which is just a simple probabilistic independence. But according to the intuition at the top, one can get other occurrences of independence by, for example, modifying these two sequences that we start off with here, using, for example, some mathematically definable functions. So I've now written down two other sequences which are obtained by modifying these sequences at the top. These are now both binary sequences. So the rule for the first sequence here is I took the first sequence on the top line, and I simply set every even position to 1. So the odd positions are the same, are inherited from the previous line, and the even positions are set to 1. Whereas on the right-hand side, I'm simply applying the characteristic function of the 6. So I'm just flagging those places in which a 6 was rolled on the dice. Once again, these are still independent in the sense at the top, because the sequences have been generated by using independent random data on both sides. The last example of sort of trivial independence is that anything in the universe is independent from anything definable. So any x is independent from pi, because, well, x might be generated using whatever randomness is needed to generate it, but no randomness at all is needed to generate pi. So it's a trivial notion of independence. I mean, certainly our other mathematician or agent could generate pi. Okay. Once we've got the independence relation, I'm being intuitive at the moment. I haven't axiomatized the independence relation yet. But once we've got the independence relation, we can give what I think is a very sensible and intuitive definition of randomness. So for the moment, although I'm going to generalize this next week, At the moment, I'm just going to talk about randomness of binary sequences. And by random, I'm going to mean random as if it were a sequence generated by an repeated sequence of fair coin tosses. And the idea is that you generate a sequence randomly, then you should satisfy any probability one law as long as that law is independent of the sequence. So this goes to the intuition that that was mentioned in my abstract, if you test randomly generated data using a probability one test that is specified independently of the data, then you will eventually observe, it makes sense to say then the test is satisfied. And so the displayed maths at the bottom just says exactly the same thing, but I'm introducing the mathematical symbols. So I'm saying R is random, meaning a fair random infinite sequence here, if and only if for all subsets of the reals, if the probability of the subset is 1 and the subset is independent of the sequence, then the random element belongs to the subset. There's a sort of question here of, well, when we're assigning a probability to a set, which sets are we ranging over? Are we looking at Borel sets or measurable sets or something like that? I'm going to leave that question till later. But for the moment, we can just think that as long as X is a set we can assign a probability to, then this is a good definition of randomness. Okay. So let's now, with our independence relation and our definition of randomness, go back to the example that I had on the prologue slide. So we started with two independent random sequences, R and S. So we can now say that we have an R and S, which are infinite sequences of zeros and ones, such that R is random, S is random, and S is independent from R. So then, well, I haven't given the axioms for independence yet, but one of the consequences of the axioms from independence is that if you have any x independent from y, and you've got a set theoretically definable function, so mathematically definable, so by that I mean the definition of f doesn't depend itself on x and y, then independence is preserved. And that's in keeping, that's a sound principle in keeping with the idea, the informal idea I presented for independence. So using that, well, here we apply, we've got S is independent to R. Here we apply the constant function that always returns the set of sequences without the infinitely zero sequence. And here we apply the function that takes any sequence S and removes it from the set of infinite sequences. We get that these independence relations are preserved. So this set is independent from R, and this set is independent from R. So by our definition of randomness, here we've got two probability one sets that are independent from R. So R belongs to both those sets. So indeed, R does belong to the sets that we wanted them to belong to, the second and third statements on the first page. On the other hand, of course, we know that R does not belong to the set of all sequences with R taken out. And, well, what this can tell us, we're going to essentially do the above reasoning, previous reasoning backwards. So because R doesn't belong to that, it follows that this measure one property cannot be independent of R. Otherwise, because R is random, R would have to belong to that set. So we must have that failed independence. In which case, again, by the preservation of independence by definable functions, we get that for any random sequence, R must be not independent from itself. So this is going to play an important role later. So for every random sequence, we're going to have that such random sequences are not independent from themselves. And actually, this notion of a sequence, of an element being not independent from itself, I'm going to call that an uncertain element in the universe. So the idea was we had random sequences have some uncertainty in them. If you've got something that's not independent from itself, it means there must be some randomness in it that wouldn't be allowed to share. That is why we can't have independence. So therefore, there's some uncertainty in R. Okay. So with that, that's essentially the end of the prologue. And we now can go to the technical development. So the technical development, these are the axioms for independence, and they're very simple, apart from the fourth one, which looks a little bit complicated, but is actually not that complicated. So I'm going to talk to you when we get talked through it. So the first one, like with pi, anything is independent from anything definable, but it's enough to just say our binary digit 0. Anything's independent from the binary digit 0, which is of course definable. A symmetry for independence. So this property, the third one, I'm not going to use. It has a strange restriction. It's about moving a y from one side of the independence to another. It has a strange restriction that in my model, I can only make sense of this for y being an infinite sequence, or more generally a tuple of infinite sequences. I haven't put that generality here. I'm including this axiom because it occurs in several axioms of independence. And it's it's a property that's needed to use the binary notion of independence to define to show that it induces a good notion of mutual independence for more than two entities. But I want to not talk about this too much now, because when we come next week to the notion of conditional independence, this property will actually follow from some more intuitive properties of conditional independence. The really interesting axiom, and this is an axiom that is I think captures an important first order property of independence, is this axiom I4. And this axiom is the one that generalizes it implies this preservation of independence by a definable function. But it's a bit more general than that. So the idea here is, well, we think of phi as a function giving us y in terms of x, but it's not just it's a multi-valued function. It can give us like lots of y, but you at least get some y depending on x. But we're requiring, there's a meta-mathematical requirement here that the definition of phi depends only on x and y. We're not allowed to use other things in the definition of, suppose we'd assumed some random element somewhere else in what we were working on, we wouldn't be able to use that in the definition of phi. But the point is, given that, thinking of phi as a multifunction, in a sense, applying phi as a multifunction to x preserves independence of x from other things, in that whenever we have a z such that x is independent of z, then we can apply phi as a multifunction to x to get some y prime that is, again, independent of z. So we're not saying that every value of y that we get from applying phi as a multifunction to x is independent of z and is independent of z. But there, at least if there existed such a y in the first place, there has to exist a y prime that we get via phi from x that's independent of z. So any existence guarantee can be, if we've got an existence guarantee for a y given x, then if we put x in, we find that x is independent of something, we guarantee to have that existence guarantee preserved. Okay, and as I've already said, these axioms will later be subsumed by axioms for a more general conditional independence relation. Okay, so to give you a feeling from the axioms, I'm going to do, and because I've got two talks, and I hope this is okay with you. So normally, when I've talked on this material in the past, though it's never been quite at this stage of development that it is today, I've basically given the headlines, but I actually want to take you through some arguments today to give you a feeling for how this independence relation works. What I want to head towards is actually, something I want to cover today is, as I mentioned in the abstract, it's going to be a consequence of having our independence relation that the axiom of choice necessarily fails in our set-theoretic universe. And I think that's a very interesting fact. We're forced, just by having independence and wanting some randomness, we're forced to reject the axiom of choice. So I'd like to take you through the argument of that. And it requires a little bit of preparation, but the preparation also allows us to appreciate this independence relation a bit more thoroughly. So as I've already said, I'm going to say we've highlighted the fact that any random element is not independent from itself. And I've already said I'm going to call such elements uncertain, because there's some uncertainty in them. On the other hand, if you've got an element that is independent from itself, I'm going to call such an element determined. The idea if something's independent from itself, then there's no randomness in it, so to speak. One way one can get an element that is independent from itself, a determined element, is if you've got any value x that's definable is mathematically definable by a set-theoretic formula. So if you've got a formula in our language of mathematics that only has such that only one element satisfies it, x, then that element is determined. I haven't put the proof of that, but essentially it follows from the fact that x is independent from 0, and by axiom I4, this independence is preserved by definable functions, and if you've got a definable element, there's the definable constant function that will map 0 to that element. Okay, so the element, yeah. So that's how the independence is going to be preserved. Lemma B is the second property is that if you have a determined element, then every element y of the universe is independent from the determined element. So from the axioms, it's clear that if we have a definable thing, again by axiom 1, we've got anything determined, we've got the constant function, and the preservation of independence will give us that x is independent. So if you've got something that's definable, then any x is independent from something that's definable. But more generally, definable things are special cases of determined things. More generally, for any determined x, everything in the universe is independent from anything that's determined. And I want to take you through this proof to show you a flavor for the way that one reasons with these axioms. So we want to prove that if x is determined, then every y is independent from x. So what we're going to do is, suppose we've got an x that does not satisfy that property that every y is independent from it. So in other words, suppose we've got an x for which there exists a y that's not independent from x. We're going to show that such an x is not determined, that is, it's an uncertain element. So suppose x is such that there exists a y with y is independent from x. Well, this statement is one of these formulas phi x y giving a multi-existence of some y's relative to x satisfying a property. So by our axiom I4 that says independence is preserved under such existence statements, for any z from which x is independent of, there's going to exist a y satisfying this property that's independent of z. So for any x that's for any z that x is independent from, there exists a y such that there exists a y independent from z that satisfies the property, so that y is independent from x. But now, well, this is for any z at all, so we can simply set z to be equal to x, and we read this out, we simply get that if x is independent from x, that is, if x is determined, then there exists a y with y is independent from x, and y is not independent from x, which is, of course, a contradiction. So what we're saying is that we're saying that x cannot be determined. So x is uncertain as required. Okay, so I'm going to take you through one more lemma of a similar kind, and then we'll get to the proof that the axiom of choice is refuted. The lemma of a similar kind, with quite a similar proof to before, states this property, which is quite intriguing in its own right. This says if we have a set X that has an element that belongs to it that is independent, that can be given independently from the set. So any such set X we can view as sort of strongly inhabited in a way. It's not just that there exists something in it, but there exists something in it that can be specified independently from the set. So a singleton set containing a random element would not be such a set. That would be inhabited, but not in this strong sense. This is inhabited in a strong sense. If you've got such a set, then it's even more strongly inhabited in that we can strengthen this independent requirement however we want. So for any y whatsoever in the universe, we can find an element in the set that's independent from that y. So it's sort of bootstrapping independence properties in some sense. You start off with a basic independence property, and you can get an arbitrarily stronger one. So to prove this, well, let's assume we've got such a set that contains an element that's independent from it. And we're going to do a similar proof to before by contradiction. So we're going to assume that the conclusion we want to prove doesn't hold. So suppose for contradiction that there exists a y for which there is no x prime in the set that's independent from y. So now this is again an existence statement. Now this existence statement now concerns the set capital X and the element y. So we've got for all expressed by it's an existence statement satisfying a formula phi of capital X and little y. And again, we can apply our axiom I4, which tells us that this existence statement will be preserved for any z from which the set X is independent. So I'm going to just take z to be the element X itself. And because because the set X is independent from the element X, this existence property is preserved for the set X. So there exists a y that is independent from the element little x that satisfies the property that we had, which is that x prime that there is no element of the set X that is independent from y. But we now see that the element, right. So we found a y for which there is no x prime in X, such that x prime is independent from y, but X is an element, little x is an element that belongs to X and is independent from y, which contradicts the fact that what we've derived here, that there is no such x prime. So that's a contradiction, and we've proved the lemma. Okay, so so getting to the end of the technical part, and then we'll get back to more conceptual development. I now want to prove that the axiom of choice fails. And the proof here is essentially the same as proofs that occur in Michiel van Lambalken's work. My axiomatization is different, but the argument so it's essentially his argument that goes through using my axiomatization. And what I'm going to show is that if we don't have the axioms that tell us there does exist such a thing, but we already saw that any random element will be, any random sequence will be an uncertain element of the set of all sequences. And I'm just saying if we do have an uncertain element, then the set of all sequences has no well ordering. And in fact, we could replace the set of infinite sequences here with any other set that we can define in set theory, but I'm just talking about the set of sequences because we know that our theory of randomness is necessarily going to give us uncertain elements of the set of sequences. The random sequences are going to be such. So we're going to contradict the well-ordering principle for the set of infinite sequences, which of course means if this set has no well-ordering, then the real numbers have no well-ordering, because this is obviously in bijection with the set of real numbers. Okay, so to prove this, we want to show that the set of uncertain we want to show that the set of infinite sequences has no well-ordering. So let's write UNC for the set of uncertain sequences, and by the assumption it's inhabited. And since the set of sequences is definable, anything is independent from it. So we've defined it by a formula, so it's definable. So in particular, our uncertain element R is independent from the set of uncertain sequences. So we're now in the situation of lemma C, where we have an element R that belongs to the set of uncertain sequences that is independent from the set of uncertain sequences. So applying lemma C, we can strengthen that independence for any Y. We've got an uncertain R prime that is independent from Y. So in particular, for the element Y that we're going to consider independence from, we're going to suppose we have, I'm not yet assuming that a well order exists, but if we're given a well order on the set of sequences, so given a well order on the set of sequences, this principle here, well, instead of R prime, I'm writing S now, tells us that we have an uncertain sequence S that is independent from the well order. So because there exists some element of the set of sequences satisfying a property, there is, of course, a smallest such element in the well order. That's the defining property of well orders. So let S be, so there is a smallest there is a smallest uncertain S in the well order that's independent from the well order. So what this description gives us is a function that we've defined. So we've given a definition of it. So it's a definable function that takes as argument any well order on the set of sequences and maps it to the smallest in that well ordering element S sub the order. So just to give a note, have a notation for the function that is uncertain and is independent from the order. Okay, so we can now get the contradiction we want. So suppose there actually does exist a well ordering, which I'll call the order prime on the set of sequences. So by the paragraph above, if we apply that function to it, we get the element S order prime, which is the smallest in the well ordering uncertain element that is independent from the well ordering. I've just written that the other way around, but independence is a symmetric notion. So again, independence is preserved under the application of any definable function. So in particular, we had a definable function mapping a well ordering to this uncertain element depending on it. So we apply that function to the well ordering here, and we get that this element S, the ordering is independent from itself, meaning that it's a determined element, not an uncertain element, and this contradicts that we were finding it from the set of uncertain elements. So this is, I think, a proof that's worth reflecting on, because it's got a serious consequence here. We have to reject the axiom of choice. But I wanted to give the proof so you can see, well, firstly, that the logic is impeccable, of course, but also from that to give you a feeling for why choice fails, because lots of people are very wedded to choice, and I am if I want to do certain things that rely on it. But on the other hand, for having a theory of true randomness, it doesn't seem very helpful to have choice, especially since we can refute it. So what we're going to do is we're going to reject choice. We're forced to reject choice. We're going to take set theory with, well, we can, as it turns out, have dependent choice, the axiom of making countable dependent choices. I'm not going to tell you precisely what that is today because we won't need it, but it's just, we can have that. So we're now making our axiomatization more formal. We're going to, take set theory with membership and independence as primitive relations and add the axioms for independence. And we're going to now extend that with the further axioms we need to develop the notion of randomness. We already have a definition of randomness, almost, but one thing I didn't say is which sets we were going to we were going to measure, find probabilities for. So let's address that now. And because we've given up the axiom of choice, we've only got dependent choice. Well, it's well known that one can have much better measurability assumptions if one rejects choice. One can assign probabilities to all sets. So Solovay would tell us we can do that in a Lebesgue measurable way. That's actually my model that justifies this. We can't just simply have Lebesgue measure. So I'm going to do something a bit simpler, but so less powerful than Lebesgue measure. But I think so. I'm going to try and talk you through this. I think this is quite a naive, quite a plausible naive approach to having a probability measure defined on all power sets. What I'm going to ask for, let's just skip the middle paragraph here. I'm going to ask for a probability measure defined on all subsets of the set of sequences that satisfies the following property, which is weaker than being Lebesgue, than being Lebesgue measure. So what I'm going to ask for is that any subset has a probability, and that the probability of that subset is close to the probability of a Borel set. So in the sense that there exists, for any subset, there exists a Borel set that has null symmetric difference with the, where null just means probability 0 according to this probability on subsets. If null meant outer measurable, if null meant null in the sense of has outer measure 0 as it normally does, this would coincide with Lebesgue measurability. But here, null just means has probability 0 according to our function, and this is weaker than Lebesgue measurability. But I think this is a nice definition, because an equivalent definition is something that's very concrete, which is, so the way I like to see this as we're trying to do some axiomatic theory of randomness, some natural mathematical theory of randomness as best we can. And in developing a mathematical theory, mathematical theories are they're necessarily idealizations of the real world. And sort of my motivating philosophy here for myself is to try and make the most ideal idealization possible, but in a sense that but only in a way that every idealization gets tied down to something concrete as best as possible. So the best way of expressing what the concrete statement that this near Borel property is equivalent to is that for any subset at all, then we can approximate that subset closely to within any epsilon by a, well, here I've written a clopen set. That's a set that's both closed and open in the product topology on the set of sequences, the normal topology on the set of sequences. But such closed and open sets are more easily understood as just finite unions of cylinder sets, the basic sets that one normally uses to define the topology, and also to define measure of the probability measure on such sets. So every subset is approximated to within any level of closeness by a finite union of cylinder sets. So this is saying, however abstract the subset, we can get close to it by a very concrete, in fact, decidable in a sense set that a set of a very simple form. And the axiom of near Borel measurability simply says that we have a near Borel measure that assigns the probability we would like to cylinder sets. So the probability of tossing any finite word of length of the word of coin tosses is 1/2 to the 1/2 to the length. And I've already these bullet points here. So the existence of the probability measure on the full power set is a mathematical idealization, but this approximation property is making it as a connection to the real world, if you like, and that this condition is weaker than asking for a Lebesgue measurable is weaker than asking, this axiom is weaker than asking for all sets to be Lebesgue measurable. And to me, this makes probabilistic sense, this axiom, and it's true in my model. That's the other thing. So we're almost there to the axioms. We still need to look at the notion of randomness. We can now define it because we've now got the probability measure. So given our probability measure, we simply define a sequence to be random. It's exactly the same definition as before for any subset whatsoever now, if the subset has probability 1 and it's independent from the sequence R we're looking at, if it's a random sequence, R will belong to that set. There's a contrapositive way of looking at this at all, which is also useful in certain circumstances, which is if we have a subset, if we have any subset of sequences, and we have an element belonging to it that's so an element is random, a sequence is random if whenever it belongs to a set that is independent from it, the probability of that set is necessarily greater than 0. So for a random element to belong to a set that it's independent from, this kind of strong notion of belonging to a set that we already used in this lemma, a random element can only belong to a set in that way if the probability of the set is 0. So once again, we've got a tension, if you like, between very abstract notions and more concrete notions. So this is, for me, the ideal notion of randomness. We've got a probability assigned to all subsets, and we want something to be random in the strongest possible way. At the same time, we want to tie it down to something that makes real world sense. So I'm essentially going to borrow the notion of Martin-Löf random test, or non-randomness test, because if it's a Martin-Löf test, you test for the non-randomness of an infinite sequence, only throwing the computability theory away. So a statistical non-randomness test is simply a collection of open subsets of the set of sequences whose probability tends to 0. So a converging such sequence whose probability tends to 0. And the idea of this is you can use such a test to test non-randomness of a sequence in the following way that, so you're given some sequence S, and you want to test that it's non-random, and you say, okay, well, I'm only interested in, I don't mind making a mistake with probability 1/2 to the n or something like that for some, I don't mind some very small probability of mistake. So I then find some appropriate open set whose probability is smaller than that of the threshold of error I would like, and I check to see if S belongs to that open set. Because we're checking to see if a sequence belongs to an open set, we can do that in finite time. And if we come back satisfied that S belongs to the set, we can say, hey, well, that looks like S is not random to within that. If it were random, there would have only been that very low probability of seeing that test satisfied. So then the collection of the whole sequence of opens is a test, and the sequence itself satisfies the test if it satisfies all the approximations, as you like. And this is a legitimate test for non-randomness, because with this definition of randomness that I've given, if we've got a sequence S and it satisfies a non-randomness test that is independent from the sequence, so we replace there's no computability, but kind of the idea of computability is here gets taken by the independence of the test from the sequence. We only test sequences using tests that are independent from the sequences. So indeed, if an S does satisfy a test that's independent from it, then one can easily prove that S is non-random. Now, what would be nice is if any non-random S can be tested. So that would be, we've got the most ideal form of randomness here, but that would be making the ideal form of randomness.
Yes, please, come in. Martha, how are you? Sorry.
Yeah.
Sorry.
Yes,
I can't. But I can hear it's Millie. Maybe it's just a small thing.
yes, so
Don't worry about it, it's quiet now.
oops. Yeah, sorry, I won't worry about that. So in fact, we're going to have an axiom that says exactly that. There's another formulation of the axiom, which is that if we, well, maybe I'll just go to the axiom. So I call this the axiom of statistical testability, which is, so we've got the definition of randomness, and the axiom says that according to the first bullet point, that if we have a non-random sequence, then we have some statistical test for the non-randomness of that sequence. But there's another statement that's equivalent to that axiom. So I've also put that there. I skipped the slide on that. And that's that an alternative way of formulating this is if we redo the definition of randomness as in the form that we gave it, only we restrict the quantification to Borel subsets rather than to arbitrary subsets, then we get a potentially weaker notion of randomness. So randomness, the full definition of randomness trivially implies the Borel randomness, and this axiom of statistical testability is equivalent to the converse implication that Borel randomness implies randomness. And as I've already said, we're giving essentially, again, we've been following the same idea. We have a very abstract, the most idealized definition of randomness possible, but we then temper that idealization with a characterization by an axiom that says that there's a practical sense to that axiom. Okay, so then we get to the last slide, which is the last axiom, which is everything so far is fine, but actually there don't exist random sequences unless you axiomatize that they must exist. You require them to exist. So the last axiom is that there exist random sequences, and not only one, but there need to exist enough of them. So what does enough mean? Well, again, we've got the most abstract statement, which is that for any subset, whenever you have a probability, a positive probability set, there must be some random sequence that belongs to the set. Moreover, there's such a random sequence that's independent from the set. And not only that, we can strengthen that independence to independent from everything. I mean, going from 3 to 4 is just an application of our bootstrapping lemma, the lemma C we had before. So that's the strongest notion. The weakest notion I can get it down to is that for any closed set of positive probability, there exists a random element belonging to the closed set that's independent from the set. So these are all 4 equivalent statements. And the axiom of enough random elements can be formulated in either way. This is sort of the one that makes you comfortable, you're not assuming too much. And this is the one that you can work with because it's the most powerful property. So just very briefly, to go from 1 to 2 is simply that Borel sets, the probability measure is irregular on Borel sets. And going from 3 to 4 is our bootstrapping axiom lemma C. Going from 2 to 3 requires a bit of work. That's going from Borel sets to arbitrary subsets. And actually, I said it was my last slide. I actually have a slide with the proof of that, but maybe I'll make the slides available somehow. So I don't want to talk through the proof because we're running out of time. But this existence of enough random elements is at the end of our axiomatization of randomness, and takes us through to next week, which is part 2 on relative randomness and the consequences of the axioms. We've finished essentially the axiomatization. So thank you very much. That's everything for today. So I mute myself.
No, I think let's just stick with your computer sound. So thank you, Alex. That was very, very interesting. So I think if I understood it correctly, there really is a very neat way of defining randomness finally, if you let go of the axiom of choice. So yeah, that's extremely interesting. So I think we can take 1 or 2 questions. We're a little bit over time, but we've still got this room for a few minutes. So if you'd like to comment or ask a question, Partha, just go ahead. just unmute Partha and speak.
Firstly, sorry for my sudden disturbance. Now for the question. You see, you added the extra property, the extra relation of independence and the axiom L1 to L4. Now, in usual NBG, axiom of choice is equivalent to existence of well-orders on every set.
Yes.
When you add this extra axioms and this relation, undefined relation, does this equivalence also go through? Because what you proved is that a particular set doesn't have a well order.
Yeah, well, I would imagine so, but it doesn't. Certainly, the axiom of choice implies in NBG, even with these you know, the additional vocabulary gives you more, not less. So you certainly don't have any original consequence of NBG. So the axiom of choice certainly implies that the set of infinite sequences has a well ordering. It probably still implies that. Well, it will still imply that all sets have a well ordering, because that's just a closed sentence. So in NBG. So the answer is yes and yes.
Okay.
Yes. So thank you for the question.
Willem, you are unmuted. Do you want to go ahead?
Okay, thank you. Just a short question. The lambda that you've defined on the power set of the Cantor space is extension of the Beck measure.
That's right.
Right?
Yeah.
To what extent is it a unique extension?
It will be next week.
Okay.
Yes. So it is when I said I'd finish the axioms, actually we need the axioms for relative randomness on top, and once one has those, it is unique.
Okay.
Yeah,
So I'm looking forward to next week.
It requires a bit of proof. It's a good
Thank you. I look forward to that. Thank you.
Yeah, thank you.
Good. Any other questions? Please raise your hand. I think we've gone a little bit over time. Thank you everybody for attending, and Alex, thank you very much for your visit. We'll stop the recording as soon as we start going off the meeting, and we'll make that recording available to people who somehow missed the talk this week and would like to join us next week. So once again, thank you, Alex, and thank you, everybody, and see you next week.
Okay, thank you very much, Beatrice, once again, and I'm going to stop the recording now.